Good evening, ladies and gentlemen. We all are here today to take part in first event of Water Forum in the year 2018. Water Forum is the water arm of IESL, addressing issues and developments in water sector of Sri Lanka with collaboration of professionals in the field. Today's guest lecture, Biological Treatment of Wastewater, Challenges and Some Solutions, is organized by Water Forum in collaboration with Sri Lanka Association for the Advancement of Science. On behalf of Water Forum, I warmly welcome our guest speaker, Dr. Maneesha Ginige. Sir, we really appreciate your generous acceptance of our invitation and willingness in sharing your knowledge with us. I wish to welcome you all, members and non-members of IESL, participating on this occasion. For the commencement of today's event, let me cordially invite Dr. Herath Mantritilaka, Head of International Water Management, to introduce the guest speaker. Over to you, sir.
Thank you. Good evening to all of you. It's good to see a large gathering here. We in the Water Forum trying to promote interest in the water sector. As you know, it's a diverse sector and a lot of lectures, publications, exhibitions are being organized. And one of the things is we trying to harness the visiting colleagues who has left us and working somewhere else and doing good. And we can learn a lot from their experiences and sort of thing. As already mentioned, Dr. Maneesha Ginige is now working in Australia for the CSIRO. It's a very prominent, well-respected research institute in Australia. It's covering a lot of aspects, and it's world-famous institute again on many aspects. So he is one of the research team leaders on that. And they are not only working on the water supply, they are working on agriculture, irrigation, and many other areas, remote sensing and so forth. So we are privileged to have Dr. Ginige here. He is actually a senior research scientist at the CSIRO, and his research thus far and focused on treating drinking and wastewater municipalities and industries. Dr. Ginige received his PhD in February 2004 from University of Queensland, Australia. Immediately after graduation, he has accepted a postdoctoral research from Advanced Water Management Centre, AWMC, at the University of Queensland. The focus of the postdoctoral fellow was to deliver to an arc linkage project titled Enhancing Biological Denitrification by Addition of External carbon sources. What, where and when was the focus of that. During this period, there were significant interactions with industry partners, especially Sydney Water and Brisbane Water, to enable delivery to the positive practical outcome to the industry. During the same period, he contributed to the development of the titrometric and off-gas analysis TOGA sensor for AWMC. As you can understand, their research is more linked to the industry, producing things to develop further their work. On completion of the postdoctoral fellowship, he joined the CSIRO in New Zealand as a research scientist with research only focus. He investigated strategies to enhance PHA, polyhydroxysiloconate, right? Oxygenate production, PHA production, using mixed microbial communities. Then he moved from engineering to the microbiology and working with the microorganisms. Subsequently, Dr. Ginige joined back with the CSIRO, and for the very first time in his career, he started engaging research related to drinking water and microbiology. The biofilms and bulk water bacteria in drinking water distribution systems, the influence on decay of chloramine, a disinfectant, and occurrences of discolored water were the primary focus area of his research. So he has been working in New Zealand, Australia, and contribution is immense. Dr. Ginige is highly focused on applied research and is concentrated on developing strategies, technologies for utilities to overcome operational challenges, reduce cost, and achieve environmental sustainability. So that's his background. I have his abstract as well, but I will not reveal that now because I leave that space for Dr. Ginige. Ladies and gentlemen, please welcome Dr. Ginige by giving me the floor is yours, sir.
Thank you for the kind introduction. First of all, I'd like to thank the Institute of Engineers Sri Lanka for giving me this opportunity to present here today. I have been developing some collaborative efforts here in Sri Lanka, and one of my collaborators, one of them actually invited me, Dr. Banduni Liyanage here, and Metika Vitanage to think about giving a presentation to you all. And I thought probably a more appropriate talk would be today would be biological treatment of wastewater, because I learned that now there is going to be a wastewater treatment plant that is going to be coming up very soon, if not already, in Colombo, and probably a topic that would be appropriate. So when we talk about wastewater treatment, most of you are engineers, you probably know all about it. So we can treat it physically, and you can treat it chemically, and you can treat it biologically. The objective is threefold. So we want to remove the carbon in the wastewater, we want to remove the nutrients in the wastewater. When I say nutrients, pretty much the nutrients that actually contribute towards eutrophication. So chemical removal is actually quite good in many ways because it is reproducible. You can apply a chemical and you can guarantee a particular outcome. And in that context, chemical treatment has been used widely in the world. But of course, chemical treatment has its own issues, such as the chemical sludge. For example, you all know about use of alum to remove phosphorus, for example, and then use as a coagulant. But what is left at the end is the alum sludge. What do you do with that? It's another headache. But biological treatment is much more environmentally friendly, and it's because it's a biological process. The sludge that is involved still could be problematic, but not to the extent of chemical sludge, for example. So, but the downside of biological treatment is the reproducibility, the reliability is a bit of a problem, but over time we have learned about biological processes. We have learned about the basics of a biological process, and that's what I will take you through today. And now we have a reasonable good handling of how to get some sort of reliability, a good source of reliability, in fact, through biological processes. And today in Australia, much of the wastewater treatment plants, I would say about close upon 80% of the treatment plants are biological treatment plants. And some of them will use biological together with chemical treatment to get the desired effluent quality. So the effluent quality is basically dictated by the EPA and so on. So the whole treatment process is driven to achieve this effluent quality, same as here. So let's have. So here This talk probably can be generalized to any waste treatment, but today I'm going to just focus on municipal waste treatment. And if you look at the municipal waste, water characteristics, as you can see, all human waste. So municipal waste is largely contains human waste, and because all human waste characteristics are pretty much similar wherever you are in the world, they are pretty much similar. So usually you would find some carbon in the form, which is measured in the form of COD or BOD. There would be some suspended solids which you need to get rid of. Then there is ammonia and phosphate. So the ammonia and phosphate is the main nutrients that is in wastewater, which needs to be which we need to get rid of. Ammonia basically can cause eutrophication. You know all about it. Phosphorus is a limiting nutrient in the environment. So if it is something is limiting and you put that nutrient into the environment, you are bound to cause eutrophication. So phosphorus is another element. If you just put it into the environment, phosphate in the form of phosphate, it is going to cause eutrophication. So the objective of wastewater treatment is basically to remove the carbon, the nitrogen and the phosphorus. So now, because this talk is around biology, I'm just going to talk about in this talk, I'm just going to cover the microbiological removal. So I'm going to talk how the microorganisms in a wastewater treatment plant, we make use of microorganisms to remove the nutrients and the carbon, and how does the microorganisms assist in this process is what I'm going to describe next. So as I mentioned to you before, the wastewater will have carbon, nitrogen and phosphorus, which we need to get rid of. So if you have carbon, how can you get rid of carbon from wastewater? You have to convert the carbon into a gaseous form, otherwise you can't remove it. So of course there are other ways of removing it as well, by incorporating into biomass, but primarily you need to get rid of carbon by converting into a gaseous form. So carbon to carbon dioxide is what we aim to achieve. Nitrogen removal, if we can convert the nitrogen, that is ammonia in the wastewater, to nitrogen gas, then we have got rid of the nitrogen from the wastewater. Phosphorus is a little bit more difficult. Phosphorus, there's no way to convert into a gaseous form, but phosphorus, we remove it as a solid. So incorporating the phosphorus into biomass is the way we biologically remove phosphorus. So let's have a look at how a bacterium could actually help to remove the carbon, nitrogen and the phosphorus. So if you take a bacterium, like a human being, it actually requires three things for it to grow: an electron donor, an electron acceptor, and it requires a carbon source. So electron donor, some of these electron donors can also act as a carbon source. So if you take an electron donor, for example here the first one is carbon. So when the carbon gets oxidized, so carbon acts as an electron donor, and it also acts as a carbon source. If you take hydrogen sulfide, so hydrogen sulfide can act as an electron donor to the bacterium, and then of course the carbon component is not there, so the bacterium will have to obtain the carbon requirement by perhaps fixing carbon dioxide. So they will fix carbon dioxide and fulfill the carbon requirement. Then if you look at the electron acceptors, so we all use, every human being, every living organism will use an electron acceptor. So what we use as an electron acceptor is oxygen. Bacteria also requires an electron acceptor such as oxygen. So the oxygen will be reduced to water, or the bacteria can use nitrate as a final electron acceptor. Nitrate can get reduced to nitrogen gas, and so on. So you can see the type of electron donors that a bacterium can make use of, the type of electron acceptors a bacterium can make use of. This slide is pretty important. I want you to really try to understand this a little bit more in detail, and just keep this slide in mind, because as you go through the other slides you will recall what I just mentioned here. All right, so now let's look at how we could remove nitrogen biologically. So we know in the wastewater, the nitrogen we find in wastewater is ammonia. So we want to convert this ammonia to nitrogen gas, otherwise we can't remove it from the wastewater. So the first step of removing it would be to get a bacterium to use the ammonia use the ammonia as an electron donor. So it will use the ammonia as an electron donor, and what would happen is the ammonia will get oxidized to nitrite, and you will get nitrite. And the carbon requirements for this organism will be fulfilled by fixing CO2, and the bacteria uses oxygen as a final electron acceptor. So ammonia gets oxidized to nitrite, and then another bacterium called the nitrite oxidizer will use nitrite as a final as an electron donor, and oxygen as an electron acceptor, and carbon as CO2 as a carbon source, and will oxidize nitrite to nitrate. So that is these two steps we collectively call nitrification. So in the treatment plant that is going to be built in Colombo, you will see that this process will happen, right? So then the second step is denitrification. So now what you're trying to do is to get the nitrate to nitrogen gas. So how can you get that to work? Now in this case, we all remember, if you remember the slide that I spoke about before, a bacterium such as denitrifiers will use nitrate as an electron acceptor, and then it will use organic matter as an electron donor and carbon source, and it will reduce the nitrate to nitrite. And some organisms can do all of these steps in one go, like nitrate to nitrite to nitric oxide to nitrous oxide to nitrogen gas, and eventually the ammonia that was initially there in the wastewater is now gone as nitrogen gas. So this is the biological approach to remove nitrogen. So what can you understand from this slide is, so there's this first step of nitrification, and if you look at that, you can see that their final electron acceptor, these organisms, for nitrification you need a final electron acceptor, oxygen. You need oxygen for this process. If you look at the denitrification, their final electron acceptor is nitrate. So they carry out this process in complete absence of oxygen. So this is the two things that we understood from this whole exercise. So now I'm going to show how people thought about to apply this in a treatment context. So what they did was, having understood the requirement of an aerobic zone, an oxygen requirement, and understood the requirement of an anoxic, that is a non-oxygen requirement, they created two tanks. So the wastewater comes in, the influent comes in, and in the aerobic tank, oxygen or air is sparged to provide oxygen, and what would happen in there is the ammonia will get oxidized to nitrate, and then there will, in the next tank, there is no aeration, so then the denitrification will happen, nitrate will be reduced to nitrogen gas, and then the effluent will be free of ammonia at the end of the day. But remember, for the aerobic tank where the nitrification is taking place, the carbon requirement is fulfilled by carbon dioxide. But in the anoxic tank, the denitrifiers fulfill their carbon requirement by the carbon that is available in the wastewater. So there's an issue with this configuration. Now it all sounds very logical, but the problem is when you actually have an aerobic tank up front, the influent carbon also can get oxidized. Remember my first slide where I showed that the electron donor can be organic carbon, and the electron acceptor is the oxygen, and they can just burn the carbon to CO2 in the presence of oxygen, right? So now for the anoxic, for the denitrification also they require carbon. By the time the wastewater comes to the anoxic zone, there is no carbon, right? And then the denitrification fails. So there is no, then you are essentially discharging nitrate to the environment, which is also a problem. So then people thought this is not good. They swapped the two tanks over. So you can see now the influent wastewater comes first to the anoxic tank and then to the aerobic tank. Sounds a little bit ridiculous when you look at it like this, because the influent has only ammonia, nitrogen, ammonia and carbon. So in the anoxic tank, there is no nitrate. You need nitrate to reduce it to nitrogen gas. So there's no nitrate in the anoxic tank. So there's nothing going to happen in the anoxic tank. And then assume that nothing happened in the anoxic tank. So the wastewater just flew through to the aerobic tank, and in the aerobic tank, the ammonia gets oxidized to nitrate. And then what they did was they put a recycle line. So you can see the top line, recycle line, bringing the wastewater from the aerobic tank back to the front. So now you are bringing some nitrate back to the front. If you bring some nitrate to the front, then obviously you are diluting some of your influent, you will dilute. That doesn't matter. But the main thing now is, now there is carbon available for the nitrate to be reduced in the anoxic tank. So the faster you bring the influent from the aerobic tank to the anoxic tank, the more nitrate the system will remove. But the configuration is such that there will always be some nitrate discharged in the effluent. But as long the guidelines are met, doesn't really matter whether there is a little bit of nitrate left. Right? So today's wastewater treatment plants, if you look at today's wastewater treatment, you will find this configuration. So this has been coming from the maybe from the 18th century. So this is very old, right? But still, this is the basic principle. So what I wanted to understand is, people didn't know the microbiology when they built these tanks. These were just trial and error kind of things. But now we understand the microbiology and the pre-requirements of the microorganisms. So we now have a better understanding of why the configuration should be the way it is today. So if we know this, if we know by reasoning, then it is easy for us to actually control the biological processes which were actually quite unreliable before. That's my point. Okay, so now we know where we can achieve nitrogen removal, right? So what about phosphorus? So the phosphorus removal also can be carried out biologically. Beautifully can be done. And I think until very recently, probably early maybe 1940s, 50s, people didn't know how to remove phosphorus from phosphorus using biological processes. Today, most of the wastewater treatment plants use biological phosphorus removal. So how can a bacterium help to remove phosphorus from wastewater? There is a beautiful organism called the polyphosphate accumulating organisms. These organisms in some ways can be even categorized as stupid, because it actually, some organisms, like if you take a human being for example, it will take up nutrients or carbon to the requirement of the body. It's not going to store some, well, of course if you eat too much then you will have a fat layer kind of sense. That sort of storage, exactly what this organism is doing. If there is more phosphate available, this fellow takes it up, stores it in excess. It not only stores phosphorus, it stores carbon. So you can see here, when the organism is exposed to aerobic conditions, that is aerobic or in the presence of nitrate. So if the final electron acceptor is oxygen or nitrate, this organism burns the fat or the carbon that it has stored as PHA. So you can see the polymer. So it has two types of polymers, the PHA, which is the carbon polymer, and the poly-P, which is the polymerized phosphorus polymer. So in the presence of oxygen, what the organism does is it burns the stored carbon and generates energy. And using that energy, it takes up phosphate from the environment and stores it in excess inside the cell. And now the other beautiful thing is, now if you expose this organism to an anaerobic environment in complete absence of oxygen, and if you put a little bit of carbon into this environment, this organism now quickly stores the carbon back into the cell. And to store some carbon into the cell, you need energy. It derives this energy requirement by breaking down the polyphosphorus that it stored before. And in the whole process, now it is releasing phosphate back into the environment. So you can now see, you can expose bacterium to one condition and get it to store. You can expose to another condition, get it to release phosphate. Right? So having understood this, now they reconfigured the wastewater treatment plant. So now let's see how you can reconfigure it. So all they did in this case, so you can see the denitrifying tanks here, the anoxic and the aerobic tank. So the second two tanks. So those are the tanks that helps to carry out denitrification. Now they introduce another tank up front, which is the anaerobic tank. So now if you think about, so the influent will have ammonia and carbon and phosphate, right? So I've forgotten to put the phosphate here, but the influent wastewater flows into the anaerobic tank, and in complete absence of oxygen, what happens in the presence of carbon? The bacteria, the polyphosphate accumulating bacteria stores the carbon. It stores the carbon that is in the wastewater. And what does it do? It actually simultaneously releases the phosphate that is inside their cell. So in the anaerobic tank, now the phosphate concentration rises. So now when the wastewater flows into the anoxic and the aerobic tanks, what does this bacteria do? In the presence of oxygen or nitrate, it burns the carbon that it stored before and takes up all the phosphate that it released before and the phosphate that came in the wastewater. So now we have removed the nitrate, we have removed the phosphate. Now where is the phosphate? The phosphate is stuck in the cell of the bacteria, right? So the effluent that goes out of after the clarifier is now deficient of nitrate and phosphate. And in a treatment plant, because the bacteria is growing, like any human beings growing, the bacteria are growing very rapidly. It just takes only a couple of minutes for a bacteria to divide and grow. So if you don't, and it also dies. So there's death and replication. So you have to constantly waste the bacteria also. So you have to waste, like you are wasting sludge, you have to waste the bacteria. So when you waste the bacteria, what happens? Now the phosphate is stuck in the biomass, you are now removing the phosphate from the system. So that is how you remove the phosphate from the system, by wasting the bacteria. Okay, so now I think it is clear how one can achieve both nitrate, ammonia and phosphate removal from wastewater. So this is something called a fluorescent in situ hybridization fish image. So here I just wanted to show here. So this is activator sludge. So in a municipal treatment plant, you get the bacteria, the activator sludge. It got numerous bacteria in there. Some are removing carbon, some are removing phosphate, some are removing nitrogen. They are all in a soup, right? So nobody is bothered about separating them. There's nothing like that. You provide the condition for their growth by providing the right environmental conditions, either no oxygen, more oxygen, or less oxygen, or so on, right? And in this first figure there, you can see the bacteria, the purple colored, actually shows how the phosphate is stuck in the cell, right? So when no phosphate is there, you can see the cells are clear. Cells are clear, right? Okay, so now I just want to show how at CSIRO we managed to develop a technology to recover phosphorus from municipal wastewater using this understanding of how the phosphorus accumulating organism helps to remove phosphorus. It's a very simple idea, and you will see it, and I think you can even figure it out yourself today. So this was the first three people. So Kayu and Anna Kaksonen are colleagues of mine, and then the Penny Wong and Sarah are the two PhD students who actually went on to do the work for us. So why bother remove phosphorus? You know, people don't think about it, but phosphorus is we dig out phosphorus from the ground, right? So it's a mineral. Like oil, if you dig something out of the ground, it's going to go. There would be a day that there won't be anything anymore, right? But the oil, no problem. We have a substitute. We can tap into the solar. But what about the phosphorus? If it is gone, it's gone, right? And then what would be our plight? Because phosphorus is a basic element of life. So if there is no phosphorus, then we are actually doomed. So then I think that would be end of mankind and life on earth. So what people have found is, or some people are calling, that we are now reaching the phosphorus peak. So here is 2016, and after some time now phosphorus is going to be limiting. If something is limiting, then the prices will go up. If the prices goes up, then it's going to affect, phosphorus price goes up, it's going to affect all human beings, right? The food prices will go up, everything will go up, right? But why should we worry about it? So the problem is also that these phosphorus reserves are restricted to certain countries. They are like oil. In Arab countries have plenty of oil and we don't have anything like that. The phosphorus are actually abundantly found in countries like Morocco, China, and so on. If these people decide to, jack up the price of phosphorus, exactly what happened after 2016 that you can see from the graph, and then everything, the commodities went up in price. So there is now a good reason that we should actually try to recycle the phosphorus we dig out from the soil. So if we can keep recycling it, then we reduce the reliance on the phosphorus that we need to dig out. Right? So that's the idea. So wastewater, as we all know, has phosphorus, but wastewater has many other valuable things like water. Water is the most valuable thing, right? And there's of course some carbon which we can convert to methane, and that could be an energy source. Then ammonia, it can be used as a fertilizer, so it's actually quite a valuable thing again that is there in wastewater. And then the phosphorus, right? So I just want to show you through a dollar value which one is much more valuable. So you can see the phosphorus is out of all, phosphorus has the least value, but it has consequences. So going to the future, we should seriously think about recovering it. So if you want to recover something from a waste source, the biggest problem is the concentrations. The wastewater has about 10 milligram per liter of phosphate. So if you want to set up a process to recover this chemically, it's not going to work such a low concentration. It's not going to be economically feasible. So if you want to actually recover phosphorus from municipal wastewater, we need to increase the concentration of the phosphate in the wastewater. And that is exactly what we try to do using biological approaches. And that's what I'm going to show here today. So biological phosphorus recovery through biological means, we are trying to increase the concentration of phosphorus, and then we can create a fertilizer such as straw white. And this straw white has been found, straw white has been found a good fertilizer because it's a slow releasing fertilizer. And there are companies such as Ostara which are now engineering to recover phosphorus from municipal wastewater and produce fertilizers for the local market. So let's see how we could achieve this. How we could use the biology. So already you know this slide. So you see when the parvos or the phosphorus accumulating organism is exposed to aerobic conditions in the presence of oxygen, they burn the carbon, the PHA, and generate energy, and then using that energy they uptake the phosphate that is in the wastewater. So now at the end of the aerobic phase, all the phosphate in the wastewater, here I'm talking about 10 liters, and if you assume 10 milligram per liter, so we are talking about 100 milligrams of phosphorus, total phosphorus that is in the wastewater. So this, at the end of the aerobic phase, 100 milligrams of phosphate is now stuck in the cell. Now if we expose this bacteria into a smaller volume, not 10 liters, maybe 1 liter, and get it to release by putting some carbon, now what happens? Suddenly you get 100 milligram per liter concentrations in this volume. So it's a very simple thing, very simple technology, and here the bacteria is acting like a sponge. So taking the phosphate from one and releasing it to another. So that is what we developed. So remember, you have seen, when you see this slide, you should be able to gather exactly what we spoke about before. So you can see the anoxic and the aerobic circles there. So you can see the denitrification configuration, so the nitrogen removal configuration. And most treatment plants around the world, actually, it's only now they are trying to introduce biological phosphorus removal. They have recognized it, but most treatment plants today have only nitrogen removal and carbon removal. They don't biologically remove phosphorus, but they are now trying to push it through. But they actually require by law to remove the phosphorus, so they adopt chemical methods to remove phosphorus. So our strategy was to introduce instead of using chemicals to remove phosphorus, we proposed this biological phosphorus recovery as a solution. Remember this configuration that I mentioned, that there will always be some nitrate discharge. So you can see the ammonia is 40 milligram per liter. If ammonia was fully oxidized, then you would get 40 milligrams of nitrate. But here you can see at the effluent, the nitrate is 10 milligrams per liter. That is because of the recycling of from aerobic to anoxic and denitrifying. So some of it has been denitrified, but about 10 you cannot denitrify it full because of the configuration. So certain countries are very strict. They want to even remove this 10 milligram of nitrate. They don't allow even that to be discharged. So in that context, then they have to carry out something called post denitrification. So at the end of here, there is in end of the treatment, the effluent has 10 milligrams of nitrate, 10 milligrams of phosphate, and no carbon. The carbon has already gone. So now to remove that nitrate, we have to artificially add carbon from external. So that is called post denitrification. What about if we can facilitate a post denitrification process, not only to remove nitrate but also to recover phosphate, and that was our aim here. So here we use the PAO, the biofilm, the polyphosphate accumulating organisms, to take up phosphate and denitrify, and then we expose the bacteria to a smaller volume to recover the phosphate. So it was a simple technology that we. So here we have we operated a laboratory scale reactor, and it's a bit of a complicated setup. I won't go through the details, but I just thought to show you the reactor setup, photo of it. So I just want to finish this story with this slide. So remember, in the wastewater, we got about 10 milligrams of nitrate, we got about 10 milligrams of phosphate. So when exposed to the aerobic conditions, the nitrate as well as the phosphate decreased down to maybe 5 milligrams or so. And then when the biomass was exposed to anaerobic conditions in the presence of carbon, you can see the purple line coming down. That is the carbon being consumed. You can see the phosphate increasing in concentration in this smaller volume. But the beauty, the second graph which I want to show from here is, if you look at the total P, the bacteria have taken, so the total P is about 60 milligram per liter at the beginning, and the bacteria actually took up, about maybe up to around 10 milligrams. Total P took up by around 3.5 hours, and then it basically released pretty much the same amount it actually up to. So it's just like a sponge. So it's the recovery is pretty good in that context. So I might just skip this one. So what we then did was, we kept on this small recovery stream. We kept on getting the bacteria to release and re-release and re-release to the same stream. So what it did was, over time, you can see the phosphate concentration increased gradually, even up to 100 milligram per liter. We were able to achieve such high concentrations in the recovery stream. Then CSIRO, using granular biomass. So granular biomass is another sort of a new technology, where the bacteria tends to agglomerate like granules. They are like rocks, and then they have unique properties of quick settling and many things. She was able to achieve almost 400 milligram per liter concentrations of phosphate, very high concentration of phosphate, using the same approach to recover phosphorus. So we have published these things in journals and so on. So now, in the next 5 to 10 minutes, I just want to go through with you on another wastewater treatment aspect, that is waste stabilization ponds. So waste stabilization ponds are, I think most of you all probably may have learned in your undergraduate studies and postgraduate studies, are a simple technology. Right? So this is an aerial view of a waste stabilization pond in Melbourne. It is so huge that it probably covers maybe whole of Colombo. It's that huge, and it actually treats most of the wastewater. I would say about 80 to 90% of wastewater generated in Melbourne. So it's a very effective, low-tech technology to remove, treat wastewater. So This is a waste stabilization pond in Jurien Bay, that is in Western Australia, that is where I am. So I just wanted to show here, so there's a new pond that is being built here. Building a pond is not just digging a hole on the ground. It is not that simple. So the biggest problem in doing that would be you will contaminate the groundwater. If you actually just put all wastewater into a hole on the ground, then you will contaminate the groundwater. So usually building a waste stabilization pond is a systematic approach. You take a systematic approach. You know, you line it with bentonite clay or concrete or things like that. You might put a polystyrene layer or something like that. Just the objective here is to prevent contamination of groundwater. So I just want to briefly go through. I think you already know. I'm not going to go through too much of details here. So usually you would have a cascade of ponds. So an anaerobic pond, the wastewater will flow to another pond, which we call a facultative pond. It will flow to another one where the maturation, where the wastewater will sit there for a while, and then eventually it gets discharged. So I just want to take your attention to the facultative pond. The facultative pond, usually you will see the color of that wastewater to be green, and that is basically because of the algae that is growing in these ponds. So there is algae, there is bacteria. They are working together, and we actually call it a mutualistic relationship that these two organisms have. What is this mutualistic relationship that they have? The algae photosynthesizes during the day. It provides the oxygen for the bacteria to oxidize the carbon that has come from the wastewater. So the bacteria oxidizes the carbon using the oxygen that the algae produce. In the whole process of oxidizing carbon, you remember the second slide. So carbon will be used as an electron donor, and that will go and produce CO2. Then the CO2 is going to be used again by the algae to photosynthesize. So it's a mutualistic relationship between algae and the bacteria. So the amount of bacteria that is in the pond is regulated by the amount of algae that is in the pond. If there's a lot of algae, there will be a lot of bacteria. If there is less algae, there will be less bacteria. So it is important to realize here that what are we trying to do here? We have some wastewater coming into the pond, and it has certain amount of carbon. We just want to only oxidize the carbon that is coming into the wastewater, not the carbon that is generated by the algae. So that is not the objective. So ideally we should have the right number of organisms, bacteria, to oxidize the carbon that is coming in. So there should be some sort of a control on the algae that is going in the pond. Otherwise the whole thing is going to fail. So then you will get effluent discharging with carbon. Not only the carbon that came in as the influent, but the carbon that has been generated by the algae, and it could be toxic. If it is cyanobacterial toxins, you're asking for trouble, right? So anyway, there was a wastewater treatment. There's a utility called the Water Corporation of Western Australia. They wanted us to do some research on. They didn't think too much into this. So they said, okay, we are getting algae discharge in the effluent. It's a big headache, and the algae goes into the lake, and the lake is becoming toxic, and the people are swimming downstream, and they might get cyanotoxins and all these sort of problems. So they wanted to somehow develop a technology to trap the algae and deal with it. So what they had done is they had created a rock filter. So they put some rocks into the big rock, then small rocks in between the big rocks, and so on. And they put it, and then the algae was trapped, but only for a short time. After some time, the rock filter got blocked. So then it didn't work. Then they had to pull out all the rocks, clean, and then put it again. Right? So it was a bit of not a successful story. So then we thought, how about we try to create a self-cleansing filter? So now I'm just going to talk to you about the self-cleansing filter that we developed. And it is actually a electrochemical system. So electrochemical system. So as you know, in electrochemistry, you would have an anode, you will have a cathode, right? So in a biological electrochemical system, you will have a bacterium growing on the anode, or maybe growing on the cathode. And what does the bacteria do? is actually helping the electrochemical process. So you know about the activation energy requirements for a particular reaction to take place on the anode and so on. So the bacteria will reduce the activation energy requirement for a reaction to take place on the anode, or if it is on the cathode, on the cathode. So in this example, you will see we are trying to oxidize the carbon. So the carbon is the electron donor and the carbon source for this bacterium. But what is the electron acceptor? So there is no electron acceptor. So I haven't shown here electron acceptor, but the electron acceptor here is the anode. The electron with the inert anode is the electron acceptor. So now the electrons are stuck in the anode, and then if you put an external circuit between the anode and the cathode, you will see the electrons will pass to the cathode, and once it is on the cathode, oxygen will act as the final electron acceptor, and then the circuit will be complete. So in this context, you will actually be able to generate some electricity as well. So again, I just want to show here just graphically, so you can see the electrons migrating through to the anode and to the cathode, and then in that context. So then there is also a possibility to get something that is thermodynamically not feasible to take place on the cathode. So usually the things don't happen if it is thermodynamically not feasible, but if you put some energy to the system, then things that didn't happen before you can make it to happen. So by investing some energy, a little bit of energy, you can make certain reactions feasible. So these are the beautiful things that you can do with electrochemistry. So so in our innovation was two-stage. So our innovation has two stages, right? In the first stage, we have an electrolysis cell. So the electrolysis cell, so you can see the abiotic cathode and the abiotic anode, right? So there's no biology involved in this first cell. It is an electrolysis cell. So because it is an electrolysis process, the influent wastewater comes into the cathode. So as you know, right? As you know, maybe I'll show you the previous figure. So when some reaction is happening on the anode, the pH goes down, the pH decreases. A reaction on the cathode will increase the pH. So just keep that in mind. So in the electrolysis process, the wastewater comes into the abiotic cathode, and now we are applying some electricity to carry out the electrolysis process. So what happens now? The cathode, the pH will rise. So when the pH rises, what happens under alkaline conditions, and the influent, of course the influent will have algae. So the algae gets trapped in the cathode. We are applying some potentials, and then the alkalinity increases, and the algae lyses because of the alkalinity. So the pH is around 12, the algae lyses. And what happens? The soluble carbon content, the algal solubilizes, and the soluble COD increases in the water. Then what happens in the abiotic anode is that the pH, like any anode, the pH decreases. So now you get acidity in the abiotic anode, alkalinity in the abiotic cathode. Now in the second stage, we have a BES, a bioelectrochemical system, a bioanode. Now here we have the bacteria alongside the anode. So in the anode, what will happen in the anode? The pH will tend to decrease. So, but what is coming into the anode is alkaline hydrolyzed wastewater. So when the acidity and the alkalinity neutralizes, and because the algae has been hydrolyzed, and now it is much more bioavailable for the bacteria to oxidize, the biobacteria on the anode will eat up the carbon, and the carbon will be, the algae will be converted to CO2, and then the wastewater that is going out would be neutral, right? And if you look at the cathode on the BES, you will see the alkalinity will increase, but the acidity in the previous electrolysis cell will neutralize that. So you can see how harmoniously these two will work to destroy the algae that comes in. So we went on to then design a reactor configuration, so to facilitate this. So it's a pretty simple reactor configuration. So just if you go to the bottom figure here, where you can see two cylinders, so you can see one cylinder inside another, And the cylinder is sort of made out of stainless steel. A mesh is welded to a ring on top, so just to form the cylinder. So the outer cylinder, what we did was we wrapped it around with a graphite felt. So the graphite felt now acts as a filter. And then the inner cylinder, we wrapped it around with a cation exchange membrane. So normally in an electrolysis cell or electrode cell, you will have a ion exchange membrane. So this is the cation exchange membrane. And then we put one cylinder inside another. So then we can define either the outer cylinder to be the anode or the inner cylinder to be the anode. It's all up to us to decide which one we want. So in stage 1, what we did was we decided that the outer cylinder would be the cathode and the inner cylinder would be the anode. And in the second stage, we swapped it around, and then it will be the outer cylinder, the anode, and so on. So now you can see, so the wastewater basically flows into the bottom, and then pushes it through, way through the graphite felt, trapping all the algae in it. And then the alkalinity hydrolyzes it, and the hydrolyzed carbon flows through to the next stage, and the oxidation takes place. So I just have one more slide, actually 2 more slides. So I just want to show here that if you don't have any potential, so this is on stage 1, the electrolysis cell. If you don't have any potentials applied, so you can see the black line at the bottom, if there's no voltage applied, then the pH that is in the influent would remain the same. So there's no change to the pH. There's no change to the soluble COD that entered the system. But if you apply a voltage, then you can see, now if you apply 3 volts, you can see there is a minor increase of pH. So the more the voltage that you apply, the higher the pH gets. And at a pH of around 12 can be achieved by applying a voltage of around 10 volts into this particular system. And we were able to hydrolyze most of the algae that came. This is a very busy slide. I probably don't think I would go through it, but I just want to show here very briefly that in this we have tried applying 6 volts and 10 volts to our electrolysis cell, and then you can see we have tried maintaining different hydraulic retention times in the tank. So and what we got from this data set, or what we understood from this data set, was first that we can attain neutrality of the effluent at the end of stage 2, and that we were able to remove like almost 100%, all of the algae was able to be trapped in the, so all suspended solids were removed. Then soluble COD increased. So the soluble COD at the beginning in the influent was very low because it was just algae, but after first stage the soluble COD increased to around 70%. So that shows that the system actually worked in lysing the algal biomass, and total COD removal was about 87%. So not all of the carbon that represented the algae was removed, but about 87% was removed. So that means we will have to backwash the filter from time to time, but not as frequent as one would expect, because 87% of the algae was actually hydrolyzed and removed. So we have published this work also in journals. So I think that's all that I wanted to talk to you about today. So if you would like to ask any questions, happy to answer. Thank you for listening.
Let's take 3 last questions. Can somebody share this? So thank you, Dr. Ginige, for that very informative lecture. As you know, the wastewater sector is moving to remove water, remove energy, remove nutrients in the world. And I know personally in Europe they are spending a lot of money to recover the phosphorus, because phosphorus is becoming a very influential element in the whole system. Now, without much ado, it's coming late. Any questions, please? Yes, please, can you hold on to a microphone?
Let me introduce myself. I am from Facultative Pond. Actually, I must thank you for this very nice overview regarding the store treatment. My question is with regard to the phosphorus POA growing biofilm reactor. So, did you check different biofilm material for the biofilm formation, and schedule for the similar to USB configuration like granular sludge? I mean, why that packing material you use was very conventional. Did you take any alternative biofilm forming material inside the reactor? That's question number one. Number two is this is can lead to somewhere around, no? But the volume of the reactor is a lab scale reactor. I mean, did you scale up in the industrial scale, and do you have any experience of operating this technology in the industry?
Thanks for the question. Yeah, I think you nailed a few points which are quite valid. What we used was a calness media. So the media is actually quite big, you know. And if you think about a media, and what are we trying to do here? We are trying to reduce the volume. We are trying to so assume that this is the media that the bacteria is actually bound onto, right? Now we are trying to get this bacteria to release the phosphate that it has inside them into a smaller volume. But if the media is taking this amount of volume, we can't expose them into a smaller volume like this because of the media taking the volume itself, right? So we only after the first PhD student did this, and she managed to get concentrations of around 100, but we wanted to get way higher than that. We wanted like 400 to 500 milligrams. Then we realized that this media volume is a barrier. Right? So if we get rid of this plastic media out of the way and get the bacteria to settle like rocks to the bottom, then we can expose get them to release into a very small volume. And if they release into a very small volume, then the concentrations can be significant. So that's what we realized. So later in the second PhD student, we got them to exactly like what you said. I wanted her to actually try to get granular biomass. So this granular biomass enabled us to get the bacteria to release the phosphate into a very small volume. So that is why she managed to get 400 to 500 milligram per liter concentrations. So I think in our work, we have only tried the calness media, and we as a media to grow biofilm, and then we went straight into granular biomass. So which doesn't have a media, it's just the granular biomass. Right? And the second question was, yes. So that's a good question. So this work was primarily carried out, we had an idea, and then we carried out, and that was carried out using funds from CSIRO. So CSIRO, funded the whole project. And usually how CSIRO works is it funds, and then you are expected to find funds after that, right? So initially they think this is a good idea, and I think I managed to convince them by talking about phosphorus limitation and how the world is going to crash and all these other things. I think then they thought, okay, this is a hot topic, let's do this. But when we did this and we found a good outcome, then we went to the industry and said, okay, now would you think about funding it further? Maybe if you to set up a pilot scale or whatever. They say this is not our priority. So like in here, exactly the situation is like in here, no different to any other country. They do what is required, the minimum requirement. Right? If the legislative body says, okay, you need to remove carbon, phosphorus and nitrogen, that's it. They are not bothered about recovering anything, because all of us say we are not a business organization, we are a public utility serving the nation to achieve these objectives, this license. So they said, unfortunately, this is not the driver. So until and when the government basically says, okay, we have to start recovering, nothing is going to happen. Right? So until today, I have tried I've spoken with many utilities and so on. Nobody is interested, simply because there's no legislative requirement for them to recover phosphorus. So that is the way it is. So yeah.
Yes. Any more questions, please? Is it all clear? Or yes, Dr. Bandu.
Don't you have any clogging problems when you are doing these things? Clogging problems in when you are having such kind of facilities?
Were you referring to the filter for the algae, or were you referring to the Okay, so I think as I showed you in the results, we managed to remove. So if you think about total COD, that represents the soluble and the total COD. So it represents all the carbon that is in the water plus in the algae, right? So we have managed to remove total COD down to around 85%. So that means there's about 20% of total COD remaining, and that could be lignin type, very hard to digest, carbon. So this carbon is trapped on the filter, and eventually, over time, this will build up, and it's going to clog the filter. And but at least we operated our filter for about 2 years, and we never had to, backwash it. But we didn't do any pressure testing in terms of whether there was a pressure loss or anything like that. We didn't do that because that was not our focus. Our focus was to develop a technology where we can, hydrolyze the algae and oxidize it, a technology. So today, I think going from the P recovery story, this is a interesting and a positive outcome with respect to this algal business. So the Water Corporation of Western Australia is now investing on it on a pilot scale project. So they want to implement it now, and so it's looking very promising. So I haven't seen the dollars yet, but they have committed to it. But hopefully we will see some dollars in this year to keep the work going.
Anyone else?
We're talking about the phosphorus removal. Phosphorus, reducing phosphate can be a problem if it deposits in the minerals are very active. So don't operators think that way that removal of phosphorus is also important?
Yeah, good question. So when you have digesters, scaling is a big issue. So scaling is a result of phosphate. So usually when you talk about magnesium in wastewater, magnesium is the limiting element in wastewater. But when you have a digester, you have phosphate in very high concentrations in phosphate in the digester. You have ammonia because you have lysed all the cells. You've got ammonia in high concentration, and you may have a little bit of magnesium there because the magnesium is also an element for growth. And these three, when they get together in the right proportion, it forms struvite, and struvite forms layers and layers on the pipes, and this is a huge problem. So another reason for the wastewater treatment plants to not think about recovery. When we go and say we are going to recover the phosphorus, they say, my goodness, no, we are already having issues with phosphorus. We don't want to even go down that lane because they're scared that it will lead to more problems. So I think I think most issues come with phosphate or phosphorus deposition is when you have a digester. So if you don't have a digester, if it is just a, I think, if to my understanding, the wastewater treatment plant that is going to be in Colombo is just an aerobic plant. I think, I'm not even sure whether it is going to be removing nitrogen. I think it is largely engineered to remove carbon from, don't quote me on this, this is somebody telling me, so I don't have the facts to sort of say for sure. Somebody told me that it's just an aerobic plant where there is just sparge oxygen just to remove the carbon, that's about it. But if that is the case, it is a bit shameful because as you saw, it is not a big difficult task to facilitate nitrogen removal. Right? You just have to configure it accordingly and then you will get nitrogen removal. Right? So, and then the most important thing is the educating the people, the operator, and how and why they are doing it the way they are doing it, so that they have an understanding about what to look out for and then fine tune it as it goes. So I do a lot of these sort of lectures to operators, in there, just to educate them. They don't have much knowledge, but I try to simplify and tell them a story so that they actually know what to look out for. So I think maybe you all should think about doing the same for people here, so that they get an interest and it's their plant. You try to give them that feeling. It's their plant, and then they take care of it.
So if there's no other questions, I would like to personally thank Dr. Ginige for bringing us to the forefront of the science and the technology. I think this is where the resource recovery and reuse is very much talked about in the science and the technologies in front. And I think we can't waste anymore considered as a waste. It's a resource which we need to make use of. With that, thank you very much for coming to me. And there's a little ceremonial thing to do, so I invite you to come.
We have a gift and a memento for Dr. Ginige. I would like to invite Dr. Nitrification to present the gift.
Thank you very much again for all of you. Have a nice evening.
We have come to the conclusion of this event. I would like to invite Dr. Shiromi Karunaratne, representing SLAS Section C, to deliver the vote of thanks.
Please hang on a minute. There's vote of thanks. Please, just 2 minutes. Just 2 minutes.
Okay, thank you very much for staying back. Actually, this endeavor today is a joint collaboration with IESL and SLAS. So on behalf of Section C SLAS, it's my duty to thank you all and thank all the stakeholders who are involved in this exercise today. First, I would like to thank our speaker, Dr. Maneesha Ginige, Senior Research Scientist from CSIRO, who came all the way and shared his valuable experience with us. And I'm sure all of you enjoyed it, and I did it myself. Thank you very much. And I need to thank IESL, especially our President, Professor Niranjali Ratnayaka, President IESL, and Dr. Laksiri, the President of the Water Forum, and also Dr. Mantritilaka from IMI and representing Water Forum again, and that is from IESL,
And on behalf of Section C/President Dr. Mithika Vitanage and Dr. Banduni Atapat, who collaborated all this the endeavor today that we all were fortunate to listen to. So thank you very much for participating and for your valuable questions and interactions, and hope we will jointly organize yet another good guest lectures or maybe some other collaborations with ISL and SLAS. Thank you very much for waiting to listen to my vote of thanks. Have a nice day.